This is the first of 3 videos concerning valence bond theory. To begin with, a little bit of a preamble. Valence bond theory is a model that allows us to picture chemical bonding. It allows us to make predictions about chemical bonding. This model can be highly complex and mathematical. We, however, will take a more simplified view of this model. This simplified view, however, is highly functional and is consistent with how most second and third year organic chemistry courses present the material. Although we are taking a more simplified view, it can still be somewhat complex. I will be providing some background theory, and one of the main things I'd like you to keep in mind is that the final conclusions that we arrive at after the third video will be the most important part. Okay, so hang in there until we get to those final conclusions. Now, valence bond theory allows us to look at the nature and properties of electrons. It views electrons as having wave-like properties. This is a little bit difficult for us to reconcile given that we're usually dealing with physical matter. In valence bond theory, there's an equation which describes what we call an orbital. The square of this orbital is related to the probability of finding an electron. Boundary surface diagrams are usually used to represent the region of space where we can find the electron 95% of the time. So rather than deal with the mathematical equation, we'll most often deal with boundary surface diagrams. You can see in front of you 2 such examples of boundary surface diagrams, both for s orbitals. Both of these orbitals have a spherical orientation, and this will be true for any s-type orbital. And you will also see that these boundary surface diagrams indicate that the probability of finding the electron is greatest near the nucleus. With s orbitals at higher energy levels, such as the third and fourth, like a 3s and a 4s, the probability of finding the electron near the nucleus becomes less and less. That is, the electron's more likely to be further and further from the nucleus. 2s and 3s and 4s orbitals also differ. In addition to being larger, they also have what we call these nodes, where there are regions of space where you're not likely to find the electron. Now, the s orbital is one kind of orbital. A different kind of orbital is called the p orbital. Here we have some boundary surface diagrams representing the p orbital. One of the things that's different about p orbitals is that they have definite orientations in space. So you can see we have here representations of the 2px, the 2py, and the 2pz. Now, it's not like you can look inside the atom and see these Cartesian coordinates, but if you can find a 2px orbital, then you can be sure that the 2py would be 90-degree perpendicular to that initial px orbital, and so on for the pz. Now, we don't have any p orbitals in the first energy level, but in the second energy level, you see these p orbitals. You'll also see p orbitals in the third and fourth. They also have this somewhat dumbbell shape, but they'll be more intricate and complex. One of the things that you'll notice about these p orbitals is that there's a node right near the nucleus. So in a sense, there's no chance of finding the electron exactly at the nucleus, but rather you're going to find the electron on either side of the nucleus. So recognize that any one of these boundary surface diagrams represents the probability of finding one electron. Now, it's helpful to look at how electrons occupy these orbitals in different elements. And so we'll start with the simplest element, that is hydrogen, and we'll use these energy level diagrams to represent this. The electrons will be represented as arrows. So for instance, hydrogen has 1 electron, and we'll indicate the arrow in a certain direction, which actually indicates the spin of that particular electron. We'll put 1 electron into the 1s, so we'll put the electron in the lowest energy level for the hydrogen atom. And by comparison, if we consider helium, which has 2 electrons, we'll put the first electron also in a 1s orbital. We'll put the second electron also into a 1s orbital, but with a different spin. Now initially I showed the arrow pointing upwards and then the second arrow pointing downwards. That's not so important. It's just that in the end we have opposite spins for those two electrons in one orbital. As it turns out, nature has made orbitals such that the maximum number of electrons that can occupy orbital are 2. So if we consider, for instance, lithium, which has 3 electrons, the first 2 electrons can go into a 1s orbital, but now there's no more room for a third electron, and so the next electron will occupy the nearest orbital that's available, nearest in terms of energy, and that's a 2s orbital, and so hence we put the electron there. Beryllium has 4 electrons, and so we'll add the first 3 electrons to the 1s and the 2s, and then we'll put the 4th electron also into the 2s. We'll fill the lower energy orbitals first. Now I'm using energy level diagrams to show the spin and the occupancy of these orbitals, but we also have a shorter notation to represent this situation. So for instance, for beryllium, we might say a 1s2, 2s2 electron configuration for representing this condition. Boron has 5 electrons. We put the first 4 electrons into the 1s and 2s orbitals. We'll put the next electron in the next available energy speaking orbital, which is the 2p. You can see that there are 3 dashed lines representing the 3 different orientations in space of the 2p. I'll put the next electron in the leftmost orbital, but actually could go in any one of those lines. And I'm not saying that that's necessarily the X or the Y or the Z orientation. It'll be one of the orientations. For carbon, we have 6 electrons, and we'll show the energy level diagram like this. Notice that we haven't paired up the electrons yet. This is because the px, py, and pz orbitals are all of the same energy, and there's no advantage to pair up the electrons until we actually have to. So we say that the orbitals are degenerate. As you can imagine, therefore, for nitrogen, the electron arrangement or configuration would look something like this, where we have 3 unpaired electrons. It's not until we get to oxygen where we have to deal with 8 electrons, and now we're going to have to start pairing electrons because we don't want to be putting electrons in any higher energy levels yet. And so we put the first 4, 5, 6, 7, and then the 8th electron will be paired. Now, just like what I did before, I put the next electron in the leftmost box or line, but I could have paired any one of those electrons. For fluorine, we now are going to put in 9 electrons, and we're going to have to pair, therefore, an additional set of electrons. And then finally, with neon, all the electrons will be paired. So this is the beginning of looking at valence bond theory. In the next video, we'll see how understanding a little bit about valence bond theory allows us to understand something of chemical bonding, including sigma bonding and pi bonding.